I'll leave it there. Yeah.
Perfect. Is that that's from fixed target, I guess?
That's right. Yeah, this is a 3 GB event display from one second,
Great.
okay.
Very good. Okay, so it's just now 9 a.m. on the East Coast, and we already have more than 60 people joining. So let's go ahead and get started. So I want to thank Xin Dong from Lawrence Berkeley National Lab for speaking for us today, and Xiaofeng Lu from CCNU for agreeing to chair. So with that, I'll turn it over to Xiaofeng.
Okay. Hi. Hello, everyone. So today, actually, I'm very happy to chair Xin's seminar. Actually, it is 18 years ago when I first met Xin in USTC when I was an undergraduate student. And actually, he just become a postdoc there and graduated from USTC. And I'm very grateful his support and help actually when I am doing my undergraduate thesis at USTC, and also later doing my PhD thesis research at LBNL. Actually, he is always warm and kind and caring to others. He's acting just like a big brother in our group. So actually, Xin got his PhD in 2005 from USTC. Now he's a senior scientist in the nuclear science division at LBNL. Xin actually has made a significant contribution to the study of quark-gluon plasma through the STAR experiment at RHIC. Actually has a research interest focusing on the penetrating probes like heavy quark and leptons. It is to examine the properties and the dynamics of the QGP medium created in heavy ion collisions. And he has led important measurements on heavy quark production, energy loss, and elliptic flow to gain insight to the QGP. In addition to QGP study, actually Xin is also interested in exploring the QCD phase structure and the baryon-baryon interaction in exploring the QCD phase structure through the RHIC BES. He also looks forward to the future research opportunity at the ESC, actually. Xin has led hold the leadership roles like STAR deputy spokesperson, STAR analysis group leader, and also as Phoenix heavy flavor topic group co-convener. Also, he has done the STAR physics analysis coordinator. He has given many result-for talks at a major conference, highlighting STAR's heavy flavor result, with detector upgrade like the heavy flavor tracker and the MAPS vertex detector. And he is enabling precise open heavy flavor measurement that provide crucial inputs to understanding the QGP properties. Okay, let's warmly welcome Xin. Yeah, thank you. Now time is yours. Thank you.
I hope you can hear me okay. Yeah.
Yes.
Yeah. Thank you, Xiaofeng, for the very kind introduction, and also thanks to Daniel for the very generous invitation. It's my it's been quite a while that we worked on the heavy flavor tracker analysis in STAR for many years ago, but recently, and today what I'm trying to talk to you is about the recent studies we look into from the RHIC beam scan, and the topic actually is not in the original. I mean, we all know the original beam scan proposal is looking for the critical point, and this baryon correlation study was not originally in our proposal, but it actually attracts significant interest recently, and particularly in the sense that the role to study the baryon baryon, including nucleon interaction and nucleon-hypron interaction, and to understand the equation state that of the liquidity matter. So let me just get started. So I'm very glad to talk to you about our recent program or studies looking for the baryon correlations and how do we learn from this measurement on the strong interactions through this characteristic scattering parameters from the RHIC beaming scan program. So this, as Daniel pointed out, this first page shows just a event display from our lowest collision energy at RHIC. This code on gold collision fixed target program at 3 GeV. And you can clearly see that it's a beam hit on a target at the end of the TPC entrance. And you can see the charge track reconstruct on TPC. So with this, as low as a 3 GeV collision energy, we are able to reach to the baryon chemical potential reaching around 750 MeV in the QSD phase diagram. So, okay, let me just, let me try to go forward. Okay, a quick outlook of my the plan of this talk. I will give some brief introduction on what we understand regarding nucleon and nucleon-hypron interactions, why we want to do that, and then I want to introduce you the technique, the Femtowsky technique that we used in the heavy-ion collisions, try to learn those interactions. And I'll show you some recent measurement from RHIC beaming scan, basically the phase 2 program. And this is actually, all these measurements are only from the first data sets, 2018 3 GeV measurement, because this is also, all these are also fresh new. And we are also exploring all this measurement to utilize in all other data sets. And I'm hoping for to also to show you, we also hoping for to show you more new results in the future meetings or conferences. So those results actually including proton-proton. This is, you can say, basic important benchmark measurement, because we know that from many low energy scattering measurement, we learn a lot on this proton-proton collisions. What do we learn from heavy-ion collisions, whether we can get a consistent picture on this. And then with that, we looked further the proton-deuteron correlations. And this is all very first measurement at this at least low energies, looking for the proton light nuclear correlations. And we also looking for the hypron sections, looking for proton lambda, deuteron lambda correlations. I'll briefly also talk about a little bit of light nuclear and hypernuclear production. This is because those are all kind of formed through the nucleon and hyprons. They also carry, in my view, also similar information, and how do we put them together. And I'll talk about some perspectives from what we see in the future with BS2 and end with a summary. So then when we talk about nucleon hypron interaction, those are important ingredients to understand the structure, basics of the nuclear and hypernuclear matter. As you can see, there's different scales we see from nuclear physics. And certainly we most interested in the kind of a length scale in this region. And we do many studies looking for the structure of the nucleon, but also the interesting actually how this nucleon form nucleus and what the interaction between them. This is also critical. And because they, determine the structure, our normal matter, and also it is also critical to understand the inner structure of this compact neutron stars and the role of this nucleons or hyprons in the to the core structure of this neutron star is still to be understood. One important, I would say, feature or that triggered us is so-called hypron puzzle. Is if you consider a nucleon, this nucleon star equation state with a normal nuclear matter with proton neutrons, and you can reach to kind of 2 times the solar mass, but if once you include hyprons, and the maximum neutron star mass is get significantly reduced. And this has actually triggered a lot of discussions, because also in observation, we do see several many neutron star with 2 times the neutron solar mass. And there are many also significant development in recent years. How do we really understand this? The bottom line is basically we need to understand the role of all these neutron, hyperon, and hyperon interactions to understand this in the future. So certainly, and we talk about strong interactions, and to the basically the first principle calculation lattice QCD is one would like to certainly apply. However, it is much challenging to do this calculation at the nucleon level, just because of you can simply look at this you can say configurations for protons. You have a smaller number of combination, while for protons this while for nuclei this certainly goes exponentially. So that just the calculation is much more challenging due to the significant increased combination that computation power needed is very challenging. So so the lattice QCD calculation actually different groups take different approaches and to try to mitigate this challenge. And however, there's different methods they import. We do see also there are differences still between different methods that's also need to be understood. On the right, this is a recent summary figure on the lattice calculation from different groups on the binding energy of the light nuclei, like the deuteron and helium-3. The different calculation shows on this colored blue, red, orange colored symbols. At this, you can see this at much large pion mass, while the real data points is located here. You can clearly see there's some difference. So basically, for the lattice group, that's still also a lot of work that need to be carried out. So historically, right, to understand the nucleon interaction, this is probably textbook knowledge that we know that they can be described by a attractive potential, usually often used as so-called Yukawa type of potential, with a repulsive core which is also not, I think to my understanding, to my best knowledge, is not fully understood. But phenomenologically, we can attribute all this the nuclear interaction with this kind of potential as function of the radius between the two nuclei. And then once you have that potential, you can plug into the conventional Schrodinger equation and then solve the equation to get the eigenstate of your system. So that's I can in a nutshell the way that many phenomenology group are doing these calculations. So as I mentioned, the lattice calculations is still to do direct calculations challenging. But to really understand the many structure, we have to also rely on lots of effective field series. There's significant lots of development also in the past many decades, but still this is a still kind of a moving, rapidly developing field, and the details still need to be understood. In the low energy experiment, to understand this is also conventional, and one can use so-called effective range expansion theory to describe the scattering and cross sections. This is I think the document also many half centuries ago. Here shows a review paper from Hans Peter, and basically it could describe you have an incoming nucleon scatter with some another center, and the cross section you can describe using this so-called phase shift. This K is a momentum of the particle, and this is a phase shift of describe the final state with respect to initial state of this particle. And this can be do an expansion according to the K in the low momentum region, and then the leading term typically we call this so-called scattering length at zero energy, and then the second term is R0 is called effective range. the kind of interesting part is basically leading term. This is directly related to this low zero energy scattering, elastic scattering cross section, total cross section in this relation. So basically, you can consider this roughly describe how strong the two particle interact with each other. The example of typical example application of this in the nucleon system is, for example, in the proton and neutron proton system, and in the S wave state, you have a spin one, excuse me, spin 0 and spin 1 state, and then we know in the spin 1 state we have a bound state of a deuteron, and with the knowledge of the deuteron and binding energy, one can also do a very precise determination of these different parameters, scattering parameters, and those have very fundamental relations to the structure of this light nuclei. So those is the kind of you can say old days, the low energy scattering experiments as well. Most of them are generally well understood. So using heavy anchorings, how do we can do this actually? We use this Fantowski so-called techniques that many of you probably heard of this, because they use this to study not the beam collision dynamics, and the initial actually proposal was also to looking for this Hambry-Brown twist effect in the heavy-ion collisions for the identical particle pairs. In general, you can looking for this kind of two-particle correlation. That's very normal definition. You look into the probability of these two particle pairs in the momentum space normalized by the individual particle distributions. In the sense, if you consider these two pairs are coming from say a common source, and then they emit out from this source in this freeze out, and also they interact, they carry some interactions between them, then you can write down this correlation function. If this is also a big assumption, can be factorized with a source size, emitting source, and the interaction between the two described in these wave functions. This K star is relative momentum between the two particles in the pair rest frame. So I will talk about this later on. And experimentally to measure this quantity is rather straightforward. We do the reconstruction of the pair in the so-called same event as a correlated term, and then using the mixed event to describe the uncorrelated term, so that the ratio of these two give you the correlation function. So as mentioned, you can see the correlation function carries both the fiber information, source information, the interaction. This is in this case the most strong interaction is dominant, and they also have some cooling interaction, which I will not talk too much, because this is I think it's a well-known and unknown phenomena, but we need to plug into our description to understand also this whole correlation function. Naninsky and Boschich actually 30 years ago, 40 years ago, they applied this effective range expansion theory into this Fantowski study. And then one can really also write down the correlation function in a rather easy way. In this approach, we kind of assume in this scattering there's S wave dominant, so you can write down the scattering wave function in terms of incoming plane wave plus a scattering term, and this scattering amplitude is a very similar way as you see here in the early days old scattering experiment, but here there's a notation change. Basically, we switch the A to define F0 with a negative A in this first leading term, and R0 swap with D0. This is just some historical reason in term notation. And then for the source, often for simplicity, we assume the Gaussian source. Describe this can be a basic sphere kind of source size that characterized by this RG parameter. Then once you plug this in, you can get a very simple description of the correlation function. And this correlation function will only depend on basically your RG and D0, F0, a few scattering parameters here. So that's actually the basics that we can try to apply this to our measurement in the heavy ion collisions and see how we can understand the system. Certainly, there's assumptions here. Basically, one is I mentioned earlier. This is a factorization between the source and interactions, and that certainly need to be always tested. And then the expansion is basically at the low K star limit, so the application range of the K star range is also need to be tested. So here, in this case, this can be simplified by just a so-called scattering length F0 and effect range D0. Okay, so this is how do we, what the techniques we want to use, and in the heavy ion collision, and we try to basically extract, marrying the correlation function, and we can try to extract these scattering parameters. And certainly, first thing we can compare this to the low energy scatterings to see what how do we what do we learn from there. So why do we want to do this in the RHIC beam scan? As we all know, in the low energy collisions, the high baryon density is very high, and so there's a quite abundant of baryons in the system. I even include the nuclei or light nuclei. On the right, this is a kind of detect particle distribution from the gold-gold 3 GeV collisions. The top is the TPC DDX versus momentum. Bottom is the time of flight mass square versus momentum. You can see in this collision system, we can see lots of baryons produced in this system, including proton, deuteron, triton, and helium, or even up to lithium, beryllium. So this gives us opportunity really to look into the baryon correlations, because the system is pretty much dominated by all the baryon dynamics. It's a very significant component there. So a brief introduction on the beam scan at RHIC. Most of you probably know that we did this phase 1 studies from 2010 to 2014, and scanning these energies from down to 7.7 GeV in collision energy. This allows us to reach like a μb from up to like 400 MeV. And the beam, the lots of interesting findings. This triggered us looking further for the beam scan phase 2 program, which we divide into 2 modes. One is so-called collider mode. This is a normal operation in the RHIC doing the gold collisions. And this is we have collected collisions from 27 GeV to 77 GeV. Each energy have a statistics roughly 10 or 20 times larger than the BS1. In addition, we also added this fixed target program. As I showed in the front page, we can collide the beam, or we can actually beam and hit a target entrance TPC. In this way, we can go down further in collision energy in the center mass frame, which allows us to really further scan in phase diagram down to higher density region. And the lowest energy we have achieved is 3.0 GeV. So the beam scan phase 2 program, one of the highlights actually, or the goal we are aiming for is to search for this possible closely critical point and locate its position. I believe you'll see probably lots of new results from the upcoming CIPA conference in May on the new results from this system. Today, I'm most talking about the baryon correlations. So a brief introduction on this, also a fixed target mode we used in this collisions, lowest collision energies, and basically the target is located at entrance of TPC. You can see it's probably like around 250 micron thick, corresponding roughly 1/4 of a interaction length, and the beam is going from my side, hit on target, and then we collect the collision from here. The lower energy, in the low energy collision, the uniqueness of this part is the start TPC actually covers the collision actually roughly mid rapidity region of the collision. This is different lines corresponding to roughly the mid rapidity region for this is a 4.5 GeV, this is 3.0 GeV. So, although the star is not particularly designed for the kind of fixed target collisions, but this actually gives us opportunity to explore the high baryon density region. To best utilize this all this collision or the physics we want to explore, star also undergo a few key detect upgrades to search for the BS2, including the so-called inner TPC upgrade ITPC that can improve the coverage in the very forward region. The end cap time flight, this is using the CBM MRBC modules and installed in star. And we can also further use that to further enhance the particle identification capability in the forward region. And in the meantime, we also have the event plane detector. This is provide a trigger and also a better event plane and centrality determination. So basically, the key idea behind this is trying to improve the acceptance coverage and also particle identification. So with this, we can do a reconstruction or identification of various particles. Star and is well positioned to do all this. We mostly know we use a combination of DDX and TPC and the mass square from time flight. You can identify the stable hadrons. Now we can see including various light nuclei as well. We can also use the TPC, the tracking from TPC to do reconstruction of a resonance or weak decay particle, including the phi meson, the lambda. Lambda is particularly interested in this talk that we use that for various correlation reconstruction, and we can also do cascade. Those are the signal in the 7.7 GeV early. And we can also further reconstruct the hypernuclei, including light, this hypertriton and H4. Yeah, so let me move on to the results then. So we, by the measurement, as I mentioned, it's rather straightforward. You identify the protons with what you have here to do clean PID, and then you construct a pair and looking for the pair correlation in the relative momentum, in terms of the relative momentum K star, and also do the background reconstruction the mixed event. So this correlation is the ratio of the same event or mixed event. This shows the correlation function between proton-proton in various centrality collisions, central to roughly mid-central peripheral, and each centrality we have a different rapidity regions. And you can see this, the general features that looks similar, but they're also quantitatively is different. And I'll come to this in the next slide in terms of the information they carry. So this characteristic kind of a feature of the proton-proton correlation, you can roughly understand this in a way that in the very low K star region, this is there's a suppression. This is due to the basically the repulsion due to quantum statistics in combination of the Coulomb interaction, as they have two positive charge particles. But really the more interesting thing here, what we are interested in is this, once you include in the strong interaction, this gives you the data points shown in blue. This is a calculation using the URQMD particle position information taking from URQMD, plugging with the strong interaction calculations, and then this is calculated using fixed radii plus the scatter length F0 from the low energy experiment. You can see that blue data point actually looks pretty similar to the data. And the data here shows the different centrality beams, and the magnitude is different, which is also, this is actually indication of the collision dynamic. Just the large size will give you a smaller magnitude in terms of correlation functions. So as I mentioned, this attractive strong interaction calculation using the F0 roughly 7 Fermi, and this provide very consistent results with our measurement. Actually, this parameter is very consistent with the low energy scattering results. And we can say this is a kind of a benchmark measurement to establish what we are doing here that looks quite good. I didn't show quantitative results on the exact F0 value here because we are working on this, and then the next step is trying to do really a more good statistical approach to like the Bayesian analysis to extract both the source size and the scattering parameters simultaneously. So actually, you will probably will see more results in the coming meetings as well. So we further extend this to the proton neutron measurement, and this is actually quite a new measurement in the high density region. The data points are shown here as circles, and this is shown proton-neutron correlation in central collision and also peripheral collisions. And on this figure shown also there are two sets of calculations. One is this dashed line shows this. If you consider only Coulomb interaction between the proton-neutron with the radial parameter, one is 3, one is 4 Fermi, you can see the data points are below there. So this is actually difference is caused by the strong interaction. And if we plug into the Linsky-New-Borch model, plug into the strong interaction using the scattering parameters from the this model calculation, but those are constrained by the low energy scattering experiment as well. And you can see that provide a quite reasonable description of data. And basically, this is this by using the strong interaction model with all this repulsive interactions that also include the basically the helium-3 bound state, because this is a proton-neutron system, and they can describe our data reasonably well. Similarly, I think this analysis is getting to final. We'll be having a paper actually submitted soon, and you will see more detailed discussion in the upcoming papers. We also further did the neutron analysis. This is looks familiar, but quantity is different from the previous slide. And what is plotted here also similarly, the Coulomb interaction shown as a dashed curve, and the data points, and you can see there's a further repulsion interactions, and this is caused by the strong interaction. And then by incorporating also the strong interaction using the parameters list on the bottom here, and they can also provide here is a reasonable description of the data. And the next step, as mentioned, we are trying to do systematic Bayesian fit studies, trying to extract both the collision dynamic information and also the strong interaction parameters. So next, I'll move on to actually the correlation with hyperons, and I think this is becoming actually more interesting. And STAR actually did this proton lambda and or p-bar lambda correlations using 200 GeV collisions before. This is show the proton lambda correlation is red, and the p-bar lambda correlation is blue. And the proton lambda correlation, you can see there's an enhancement in the low K star. Excuse me. And the data points is a little bit error-wise a little bit large, but we do see that the green curve is this Linsky-New-Borch fit using the parameters from this model calculations. And at that time, we use this try to extract the collision dynamics. We expect that the low collision energy, we have much better statistics, and this actually gives us also better control. We can try to further, instead of compare with models, but rather do an independent fit to extract parameters. I'll show some results later. As I'm showing you, we have lots of also light nuclear. We can, in the STAR first did also the neutron lambda correlation. This system is particularly interesting in the sense that this probably can provide a nice information into the hypertriton structure. As hypertriton is widely considered as a loosely bound state, although it's a 3 kind of Baryon system, but it's can be more or less approximate as a deuteron core plus a lambda in this vicinity area. So this is actually this correlation function also can provide very hopefully provide information to understand the hypertriton in the structures. So we do the correlation measurement. This is a proton lambda correlation in central, mid-central peripheral collisions, and also in the 3GeV. You can see that general features looks very similar to what you see here, but now with much improved statistics. And we in this proton lambda correlation, we did actually do a very consistent non-Lensing-Lubotshik fit. And I'll mention that in this fit, what we did is using a simultaneous fit for all three different centrality beams with a different source size parameters, but the common spin common scattering parameters F0, D0. In this, although in the proton lambda case, there are like two spin states, but in here we do a spin average fit because of also we couldn't separate these two in this case. We extracted the scattering parameters on the order of 2.3 Fermi. Actually, it's very well in the range between, I mean, you can see the close in between the singlet and triplet state. And one also important thing we can see here is the scattering parameters F0 between P lambda is smaller, much smaller than the proton-proton, which is roughly 7th of Fermi. As I mentioned before, that this roughly, I can give you an idea the interaction strengths between the P lambda is weaker than the proton-proton collisions. I'll show you first, and I'll mention about the extraction parameters later on, the deuteron lambda correlation as well. And this is the first time measurement of this system. And the correlation that looks actually pretty strong. If we look at the y-x scale, this is on the order of 10 or 15 instead of previously it's like 2 here. So there's a very strong correlation between the deuteron lambda system. Similarly, we do a simultaneous fit between the different states. Here we do actually separately. I'll talk about this in detail later on. For the deuteron lambda, because of the nature and also the statistics, we are able to do spin separate states. And so in this fit, we have different RG parameters in different centralities. And we also have a two set of F0, D0 for doublet and quartet state, because these two, that's corresponding spin 1/2 and 3/3 states. And that actually, the fit looks pretty well to describe all the data points in different centrality beams. So as I mentioned, talking about the different spins. So in the S wave, between this two pair system, both the P lambda and D lambda have two different kind of spin states. In terms of P lambda, you have a singlet and triplets, and in the D lambda, you have the doublet and the quartet states. The parameters listed here are from various model calculations. The D lambda also, there are many model calculations based on the Carroll effective theory, and they provide, but they actually vary quite in a wide range. In the P lambda case, you can see that F0 is pretty close to each other between the two states. So our current statistics actually is not sufficient to separate the spin states. And we did try to do a separate spin states measurement, but they don't have really a separation power. The two states looks very similar. In the D lambda case, and we are able to do this separation. In case of the two spin states, the way we want to do is to actually replace a wave function with the two different state wave functions. They have a similar description in terms of their formalism, but the difference is basically their strengths or the way probability between these two are different. This coefficients are determined by basically the quantum statistics. On the right figure, you can see that what we plot here is fit results, the data with the total. In the meantime, also the plot the two different states, doublet and quartet states. In this insert panel is a zoom in this very small correlation region to basically show it clearly. Excuse me. And with this, we can compare the extract source size of so-called RG parameters between different systems. And this will show the different centrality for P lambda in the red and D lambda in the blue. You can see the two features. One is there's a central dependence, which is one expect from the collision dynamics. You have a large source size in the central, small source in the peripheral. And in the meantime, there's also a kind of a can say hierarchy or the ordering. The P lambda source size larger than D lambda, which is also expected if you consider they follow therefore if they're coming from the same source and then they follow this so-called empty scaling feature. And we'll do that more detailed kind of comparisons in the future study, but this is a qualitatively that looks very as expected. And so let's put all these extract parameters out here. This is what we extract for the plotted as effective range D0 as function of scatter lengths for the two systems, P lambda and D lambda. The P lambda shown as a red, although it looks very not very on Euro, but it is a truth because the red data points have very good constraint on the F0, while D0 have large uncertainties. And in comparison, the two results from the model calculations, the green data points, you can see the data points are sit very well in between. And this is a fit for the P lambda is a p-spin average. For the D lambda, we are able to separate two spin states, and that's shown as these two kind of a separate contours. This shows as a 1 sigma, 2 sigma, 3 sigma separation contour on this parameter space. The interest in the W states is in the negative region, and this is actually very expected because there's a hypertriton bound state in the D lambda system in the W state. So, and our data points actually, you can see, can provide a quite good constraint on what the model calculation on all these triangles are different model calculation on this state. While on the quartet state side, this is you can see the extract F0 and have a much better uncertainty. This also expect because they have a much larger weight, so the data point have a better constraint on this one, and our precision now can really constrain on these models. You can see the several models are more than 3 sigma away. And this is actually another interesting that learned here is also in the quartet state because F0 is positive. That is also indicating there will be no bound state actually in this excited quartet states. So hypertriton actually is the most is the ground state. This actually has an implication in terms of when we do our yield measurement and compare to the thermal model calculations. So based on the measurement here, and if we consider the hypertriton ground, this D lambda W state, and based on this this effective range expansion theory, you can using the F0 D0 parameters to calculate the binding energy. This is rather also well established formalism, and the data points are shown on the top here. And this is from the D lambda correlation, 1 sigma range, 2 sigma range. And the error bars are not a linear scale because of also the probability distribution is not particularly Gaussian. So, but you can consider this like 68% probability and 95% probability. And we compare this actually, you can see to various previous measurements. Those are the old days, this nuclear emulsion experiments. And those are the two recent measurements from STAR, at least using the environment mass techniques and to calculate lambda separation energy. And this new measurement using D lambda correlation, you can see actually they provide also reasonable precision now. And this is what we can consider as a kind of a new complementary way to understand this particle inner structure as well. So talking about this the hypertriton, as I mentioned, I want to show you one thing is we also doing lots of hypertriton measurement in star beam scan. And here I just show you one measurement on the yield dNdy for the hypertriton and also H lambda 4 for central and mid-central collisions. The curves are model calculation, the coalescence, GM plus coalescence model calculation. While in the coalescence, we all know there's a so-called this coalescence parameters. And in the case of hypertriton, you can see we choose parameters. This is also triggered by because binding energy is small, and that we choose a relatively smaller coalescence parameters in order to also to describe the data points. And so what I want to show you here is basically there's potentially also the relation that how do we really better use these coalescence parameters and to understand the so-called winding interaction. I believe there's a close relation and in these different measurements, but I think we need also helps from our phenomenologists to understand this relations in the future. So I think those are main kind of new results I want to show you, but those are just coming from the 2018 3GV datasets, one single 9 here. We have a list of many datasets on disk that to be analyzed, and there's also those datasets will also allow us not only look at the baryon correlation, we also look at the meson-meson or baryon-meson correlation to understand all this interactions between different hadrons, and also the in the structure of all these exotic particles. In the fixed static energy, this is also one specific interest, in particular for the hyperons, is you can see the hyperon yield increase dramatically from like 3 GeV up to 20, 30 GeV. So this is actually give us a chance to really try to understand the dynamics of the hyperons in this collision system. And also 3 GeV sit here, so you can expect the statistics for this hyperons at higher energy will become much better. And we are trying to further utilize all these data sets to understand this, to gain better understanding of the baryon correlations. One example I want to show you actually is we use this to search for the exotic particle. We started already looking for the lambda-lambda correlation in 200 GeV. This was the old measurement from STAR, many people probably know, and they show a suppression in the correlation function. And we do also similar Nancy-New-Borshik model fit, and you can extract this. The way this plotted is a different is the 1 over A0 is basically F0. And the data points are extract here has a large uncertainty, so indicating with this error bars and the boxes systematic errors. And in comparison with Baryon model, you can see there seem to be also ordering, because this plot is a 1 over F0. So the ordering is basically you have a F0 lambda is smaller than the P lambda than the PP. So this is actually a first try that we see actually to understand the hyperon interactions, and we will further carry this on in using the beam and scan phase 2 data sets, and those actually give us opportunity to further improve the measurement of this. We also we have started already looking at the P cascade correlation in the 3 GeV. Excuse me. This is a measurement. We released a preliminary. Error bar is still large, and but we are looking to the future, try to gain more statistics at a high energy than high other data sets. What I want to basically highlight to you is that those actually the BS2 data set will enable us to search for those various exotic particles through these baryon correlations into the future. So there are more results to come. I mentioned to you a few times that in terms of the extraction of parameters, and we are doing now a Bayesian inference analysis, and that gives us opportunity to really constrain all these parameters simultaneously. Also, not only the parameters, but also their covariance as well. So this is ongoing efforts. I don't have a results. This is just show you schematic view of the approach they're trying to do, and we thanks actually to quite a few theory friends that they released their open source code for this to help us to get this also started. At last, I'll mention that this beam scan 2 also, as I mentioned, give us opportunity to looking for the light care, particular hyperliquid measurements. And as I mentioned, this hyperliquid also that by constructing it carries information of also hyperon and nucleon interactions. And what I show here is just one measurement on this also called S3 parameters. It's a double ratio of hypertriton over light nuclei normalized by lambda proton. You can see the new measurement shown here and the energy dependence shown in this plot, this high energy Alice and star measurement. And we hopefully to further improve this precision in the low energies and for not only for hypertriton, we are able to reconstruct also the other light nuclei, the A equals 4, even A equals 5, and also hopefully have a chance to maybe further search for the double lambda hypernuclei. This could give us opportunity to study the hyperon interaction also in through this system. So let me summarize. So I hope that I convinced you that the beam scan dataset or the program enable us to also do a detailed investigation of the baryon interactions using these Minkowski techniques. We learned now, actually, at least we did the benchmark measurement with proton-proton and I extract FD0, F0, D0, very compatible with the low energy scattering data. And we can extend this to the proton-deuteron measurements. And furthermore, to apply to the with the hyperon sector, looking for the proton lambda and deuteron lambda. And we get a lot of actually new interesting results from this measurement. I want to say that this is just a glance of the new data sets we have. There are much more data to be analyzed, and this also gives the opportunity to search for the exotics and also looking for the multiple particle, like for instance, 3-particle correlation as well. This hopefully will give us significant input to constrain the strong interaction parameters between nucleon and hyperons. And but to do this, certainly we hopefully that our data will give a significant input to our theory community, including both the effector field theory phenomenologists and also lattice QCD theorists. And in the nutshell, that hopefully we can have a much better understanding into the future on all these baryon correlations to help us understand the equation state of this QCD matter. So thanks for your attention, and I'm happy to answer any questions or I'm looking forward to your comments. Thanks.
Thank you, Xin, for this very nice and comprehensive talk. So now it's open for question. Any question for Xin? Jürgen, yeah, please.
Yeah, so I have a question. So when we did comparable studies at higher energies at LHC to look for the interaction between baryons, we found it very important that one takes into account feed down. So for example, if you study proton lambda correlations, actually only 50% of the proton lambda correlations are primary particles, the rest comes all from various feed downs. Presumably that's much less of an issue in the fixed target configuration you have, but did you quantitatively look into that and do you take it into account?
Yeah, that's very great question indeed. In the proton, I mean, I just take an example for the proton lambda case. The proton, the feed down from the weak decay lambda feed down is very small. It's 1% at 3 GeV, so that's very small. And but there's one thing, the lambda feed down coming from the sigmas, and that in this analysis we did take into account using the based on the thermal model calculation. In this case, that's roughly like 20 to 25% of the lambdas coming from the sigma decays, and we did include that doing these corrections. But I think you brought up a question. Actually, when we do this correction, and currently the most approach that are assumed here is this only considers a dilution effect, and which is actually need to be tested. But that's
Okay, yeah, I think yeah, okay, so it's much less of an issue, that's what I guess, but it's not negligible. And indeed, you have to not only look at the dilution, but because you mix in possibly different MT and source sizes, you may have to go.
exactly, yeah,
Exactly. Okay, good. Okay, thanks.
Okay, any more questions or comments? Okay, this looks like very clear talk. So, so Xin, so, okay, Yifei, please.
Hi, Xin.
Hello, Yifei.
Yeah, very nice talk. I have one question on do you have any plan to measure the light hyperleucite flow in low energy data?
Yes, we do actually. I think you probably know that we publish the direct flow of the hypertriton and
Yeah, the
H9
V1 is
on
published, but
3GeV.
how about V2? Yeah.
We are doing also the V2 measurement now, and at a very low end, like 3GeV, the statistics is well, not the statistics, and also this event plan resolution is worse because we have to rely on the first order event plan to do the V2, and that's actually is statistic-wise is challenging. But we are doing that, and then there are already people actually looking for not only the fixed site data sets, but also the collider data sets to looking for both the V1 and V2 measurements. It will be probably the statistics or eventually how precise we can do. Sorry, maybe I have a slide to show that just to, yeah. So this is the right figure is what we published in terms of V1 for the light liquid and hypernuclei. And I think we need a precision to be further improved. I mean, this precision, the measurement is already very good, very statistic-wise already good, but it's still not sufficient enough because what we're looking to is really whether we can see a difference in terms of in comparison with light nuclei. And for that, we really need much better data sets. And I hope that we're exploring, hopefully the BS2 can provide some guidance, but I'm curious that probably that won't be able to answering all these questions with the BS2 data sets. Probably need more measurement into the future.
Yeah. Yeah. The related question is so since the light nuclide production is mainly from the coalescence mechanism, so one would expect a larger significant V2 because they are from the coalescence of the nuclide, right? Yeah. Yeah, if we have the precision to measure the V2.
Yeah, agree. Yeah, I think it's eventually come to really the precision we look into. Yes.
Okay. Thank you.
Okay, Jiaxin.
Yeah, very nice talk, and I have a small question. So here you use the Lindelicke-Lubosheet model, right? And which can give you a analytical formula of the correlation, and then you fit the experimental correlation function, and then you can extract the effective range and the scattering and as shown here, and the A0 and the F0. But here I want to ask is if you use a LL model, which assume that the interaction potential between the P lambda and the D lambda is a very short range potential, right? And how good of this approximation, and does it affect the binding energy of the hypertriton? Yeah.
Yeah, that's very good question. Actually, I forgot to mention that indeed, I think the approach here, as you point out, indeed, the scattering amplitude, the expansion here, this is a low K-star expansion. So the validated region, what K-star region this works, I think this is to be tested. And our approach is trying to test it out and apply this to our experimental data to see how well this can work out. In our extraction of all these interaction parameters, we do consider as one of the so-called systematic errors to fit the experimental data in different K-star region and see the impact in the extract parameters and also the impact in correlation. That is included in our total uncertainties. Yeah.
You mean the for the source term, it's related to the relative momentum, right?
The source term, yes, is right. It's a kind of a coordinate space distribution, and then it's directly related, yeah, in the K star as well. Yes, you can consider it's a kind of Fourier transformation of the of that into the coordinate space. Yeah.
Okay, I see. Okay, thank you.
Yeah, thank you, Jiaxin. Looking forward to your calculation for our nuclear and light nuclear and hypernuclear measurements.
No, no, we don't have this kind of, but recently we want to use machine learning to extract the interaction between the P lambda, D lambda, and any other nucleons from directly from the correlation function.
Ah, that's great. Yeah. You mean
because we know with the interaction potential we can calculate the scatter amplitude, then we can get to the correlation function. Then we want to do the inverse mapping from the correlation function to the interaction potential.
That's great. Yeah. That's great. Yeah.
Yeah, we can see that. Yeah. Okay. Okay, thank you.
Thank you, Jiaxin. Yeah. Any more questions for Xin? We still have time. So okay, so maybe let me ask. So Xin, do we have plan to study the three-body interaction to understand it? Yeah.
I think yes, we do. It's also coming down to the question of statistics. I don't know if you remember that we did study actually. Yuehang did look at the proton, three proton correlations already in the 3GeV data. Let me go to this slide. Actually, when we talk about statistics, it's still limited statistics, but I think I don't know whether all people knows, but I want to point out there's a 2 billion events that is of 3GeV data is coming up, and this actually give us opportunity to looking for many of these things statistic-wise. So that's a very give us a good chance to look into that. So I believe there's lots of opportunities, as I mentioned, that we haven't really fully explored this territory, and hopefully that we can do further collaboration and looking for all these various measurements. Yeah, the three body indeed. You can say we're looking for basically three particle. You can genuine correlation that is probably least long. There are some existing measurement from a least, right? And if I remember correctly, but that still precision wise is still not precise enough. And I didn't mention that in constructing this equation state, the three body interaction is a very important ingredient. At least to one of the approach that consider this is an important ingredient to really make the equation state harder to in the neutron star. So I think sooner or later we should go for that three body interactions, and I also see from effective theory there's some effort also trying to do the three body potential and to get to understanding of this as well. So definitely more data will be much more data will be very important.
Mhm, mhm.
Yeah, so
Okay.
I can confirm that we have 3 body data for PPP and
Yep.
PP lambda, I think, and I think now even with kaons. But you're right, the statistics at this point, that's from not yet including the new run, is more limited.
Yeah. Jürgen, is that I remember that's from also proton collision, or it's a lead collisions.
It's proton-proton.
Yeah. Okay. Yeah.
Because it's much easier, of course, to measure these final state interactions proton-proton.
Right. Yeah. That'd be great if that round 3 can also provide actually much more data to look into this.
Mhm, mhm. Okay. Okay. Any more question for Xin? I see. Okay. Yeah, I think there's no more question, and I'd like to thank Xin again. Yeah, I think
Thank you.
that's
Thanks
that's all for
everyone for
today.
attending, and thanks for
thank
the
you.
discussions. Yeah. Okay.
Yeah.
I'll see you all in other occasions in future. Bye.
Thank you. Bye.
Thank you,
Thank
Jim.
you. Thank you, everyone, for joining.
Bye.